Okay, welcome everybody to our last video for gas laws. And so what I'm going to talk about is gas stoichiometry, collecting gases over water, partial pressures, and then some of the KMT postulates and the root mean square velocities, and how to graph that out. So the first thing I want to talk to you about is the stoichiometry problems. So here we have a reaction in which we're trying to reduce a metal oxide heated in the presence of hydrogen gas. We produce pure metal and water. So we're doing this for copper. So we're going to take our copper oxide and we are going to heat it in the presence of hydrogen gas. We are going to produce the pure metal and water. And so they're asking you, what volume of hydrogen gas can you produce? If we write the water as H2O, then we can balance the equation. So I'll write that as H2O. And so now we have one copper, one oxygen, two hydrogens. It's all balanced, it's all 1-to-1. So they ask us what volume of hydrogen at 765 torr, 225 degrees Celsius, are needed to form 35.5 grams of copper. So this is going to be my question mark, and we'll do it in liters. So this is a straight up stoichiometry problem with a twist at the end. The twist is using PV equals nRT to try and figure out, well, so our plan is to take our 35.5 by 1 mole for every 63.5 grams, times that by 1 hydrogen for every 1 copper. And when we do that, what we get is 30.5 divided by 63.5, and I get 0.56 moles of hydrogen. Now plugging that into PV equals nRT, PV equals nRT, and solving for V, we get that N is 0.56, R is 0.0821, the temperature is in Kelvin, so we need to change 225 to Kelvin by adding 273, that's 498 Kelvin. And dividing that by the pressure, which needs to be in atmosphere, 765 divided by 760 is approximately 1. And now we can work out what our volume would be in liters. So 0.56, we times that by 0.0821, we times that by our 498, and we get a total of 23 liters. So these types of stoichiometry problems, you're either going to have to use PV equals nRT at the end or use it at the beginning, but at some point you're going to have to use it. You can't just find the moles of hydrogen and times it by 22.4. It won't work. Okay, let's try the next topic, which is partial pressures. Partial pressures rely on the fact that gases mix evenly. If you put two gases into a container, and here's my container, and I have one gas that I'm showing in purple and another gas that I can show in orange, then what I'll have is I'll have two separate gases here, and they will occupy the entire space. And their pressures will be dependent on their moles. And so I could just add the pressures together, and this is the simplest type of, the simplest allocation of Dalton's law of partial pressure. So this Dalton's law of partial pressure really is just saying, like, hey, you take the pressures of each gas, you add them together, you get the total pressure. And so this is Dalton's law. So, you could do this in a more elaborate fashion, as I show down here. Instead of having just the pressures, what if you're given the moles, the temperature, and the volume? And so what you can do is you can use an elaboration of PV equals nRT. So P1, instead of just writing P1, you substitute in N1 RT over VT. Again, the volume is always the total volume. And the volume is always the total volume because the gases will spread out and they will occupy the entire space. So the way that I can look at this, if I want to find the total pressure, I can just say, well, P total is equal to all the moles added up times R times T over the volume total. Now sometimes though I'm not given temperature and I'm not given volume. All that I'm really given is if I have, you know, the number of moles of each gas. And then I have to use a different law. And it's, based on Dalton's law of partial pressure, but it looks like this. It says that the pressure of the gas is equal to the mole fraction of the gas, which is equivalent to the moles of the gas over the total moles times the pressure total. How would that look in a mathematical type setup? Well, it would kind of be like this. Let's say, for example, that I had 3 moles of hydrogen and 6 moles of oxygen, and I had a P total of 8 atmospheres. Well, if I want to find the pressure of hydrogen, I would take the moles of hydrogen, 3, over the total, which would be 9. 3 plus 6 is 9. And then I would times it by 8 atmospheres. So that gives me 24 over 9. And 24 divided by 9 gives me 2.7 atmospheres. So the pressure of hydrogen is 2.7 atm. If I did this for oxygen over here, well, the pressure of oxygen would be equal to 6 over 9 times 8 atm. So the pressure of oxygen, which would be 48 over 9, give me 5.33 or 5.3. And so when I add these together, I get a total of 5.3 and 2.7 adds up to the total of 8 atmospheres. Now lastly, I could do a partial pressure where I have, 2 flasks connected to each other, and that's this one right here. And I like to do this one in class with you. We're going to start off tomorrow with this one, and I'll give you an example. But when you have 2 flasks connected to each other, you have to use P1V1 equals P2V2. We'll do one of those together. It's kind of cool to see how that works. Okay, another place that partial pressures comes into place is when you actually have collecting gas over water. So this apparatus that I show you here is collecting gas over water. The reaction is taking place in what I'm going to highlight right now, which is this reaction flask. And there's a gas produced, and this gas is getting bubbled in, and it's coming out here, and it's displacing the water. And so this is kind of like right at the start, and this would be right at the end. And at the end of the reaction, you can see that the flask, or the beaker, has been replaced by mostly gas. The issue is that since this is being collected over water, some of the water has evaporated and is exerting vapor pressure. Vapor pressure is exactly that. It's the pressure exerted by a gas that's evaporated. So when the water evaporates, it actually starts to exert pressure in here. So the pressure total is equal to the pressure of the gas collected plus any water that evaporated. Now the good news is that this pressure of the water that evaporated is very low. Normally this happens at around 20 degrees Celsius we do these reactions. So the vapor pressure of water is about 20 torr. The total pressure usually is about that of the atmosphere. Since the levels of water are equal, the pressure inside and outside are equal to each other, so the pressure total is usually about 760 torr. So most of it's the gas that you collected. The pressure of your gas would be equal to 760 minus the 20 from the water, and you would have 740 torr. This is one of the best ways to collect gas. The water evaporates very little, you have mostly a pure sample of gas, and it's generally enough to use in reactions or, for purification. So let's look at how this would happen in a problem here. So, let's say that I had a sample of calcium carbide and I add it to water. It produces ethylene gas and carbon and calcium hydroxide. So they have this sample of acetylene. It's going to be collected over water. The acetylene is the C2H2. Total pressure is 738 torr. The volume is 523 milliliters. Temperature is 23 degrees Celsius. Vapor pressure is 21. Find out how many grams were produced. Well, like if I collected this gas over water, I have my pressure times my volume equals my nRT. And in this case, we're solving for N. We want the moles. N equals PV over RT. Now the pressure we know, but we have to do a little trick to it. The pressure is going to be the total pressure, 738, but then you have to subtract the water from it. Will it make a big difference? It won't really make a big difference, but you still have to do it. So now we subtract the water vapor pressure and we get 717. Divide that by 760 to get our atmospheres. And we have 0.943 atmospheres. .943 atmospheres. So now we go through, we plug in our numbers, 0.943. We have the volume, we change that to liters, 0.523 liters. We have our R, 0.0821. And we have our temperature, which we need to change to Kelvin, so that would be 296 Kelvin. We plug this in, we get N, we times it by the GFM, and we get the grams. You can go ahead and do that, get your answer. So as you can see, the vapor pressure of water is not a big deal. But you have to subtract it from the total pressure in order to find out the pressure of just your gas. So that's all the math for this chapter for the most part. Let's talk about, actually there is a little bit more, but let's talk about how gases behave. And I kind of put this here because it ties in nicely to, what's known as root mean square velocity, diffusion, and effusion. So these are the postulates, and I kind of broke them up into 3 different ones. The whole idea behind KMT stands for kinetic molecular theory, and the idea behind this is that it helps to explain how gases behave at the macroscopic level by looking at them as little tiny individual particles. The first thing has to do with particle volume. So any gas that you have, unless it's in a vacuum, there's lots of particles. And the thing about the particles, though, is that their volume is really, really small. And so this will help explain why gases are compressible. If you think about a gas here with particles that are really tiny, there's lots of space between them. I can compress them. And this helps explain pressure versus volume. If I increase the pressure, I can push those gas particles together. The next thing has to do with particle motion. The particles move in straight line motion. This is called linear motion. And this really explains, I can't spell motion for some reason, this really explains pressure versus temperature. So when you increase the temperature, these particles are moving faster. This faster movement, it's going to give you more energy and more force. This force is going to give more collisions, more frequently, more forceful, you're going to get a higher pressure. And finally, the last thing is when those particles collide with each other. Collisions are elastic. What that means is that there's going to be an exchange of energy between the particles, but the total amount of energy for the system is going to remain constant. So there's no loss of energy when there's collisions, and there's no overall gain of energy. And this is really why, when you increase temperature, all of the energy changes go to the motion of the particles moving faster, colliding more forcefully. But all of those collisions, they are elastic. So there's no loss of energy. And so you get that nice linear curve when you do P versus T, and you get this constant. If we do, we should put T as the independent variable. Pressure over here, that's why we get that linear curve like this, that's direct. Now because these gases are in motion all the time, gases will randomly mix with each other. And they'll also spread out on their own accord. And so what ends up happening is, like you have 2 processes, depending on where the gas is contained. One is called effusion. And effusion is where a gas will move through a tiny little hole, like, if you had a balloon with a tiny pinhole in it, the gas would rush out. And one's diffusion, where a gas will move through another gas, or it will move into a surrounding vacuum. The equations for them are the same. How fast the gas moves is inversely related to the square root of its gram formula mass. It's called Graham's law of effusion or Graham's law of diffusion. And so if I write this out for you, so the rate is equal to 1 over the square root of the GFM. As the GFM goes up, the rate goes down. And you'll kind of see this when we do root mean square velocity, because that's where this square root idea comes from. You'll see it on the next page. Do the same thing with rate of diffusion. Diffusion is again a gas moving either into a vacuum or into another, and again you have 1 over the gram formula mass. Square root of the gram formula mass is the rate. Now what's really helpful is when you compare two gases. So we have the rate of gas 1 versus the rate of gas 2 is equal to the square root of the gram formula mass of gas 2 over gas 1. Now look, with this, we could do something like comparing the rates of, let's say, hydrogen and oxygen. So if I want to see which one, how fast they're diffusing, I could do the rate of hydrogen over the rate of oxygen equals, and then I take the square root. The oxygen goes on top, 32. The hydrogen goes on the bottom, 2. That's square root of 16. That's equal to 4. What this tells me is that hydrogen is 4 times faster than oxygen. And that's important because a lot of people do these studies with movements of gases. So, you could do any two gases, or you could even solve for the gram formula mass. They give you the rates. If they say that a gas moves 2 times faster or 2 times slower, you can make the other gas equal to a rate of 1, and then 2 times faster would be 2 over 1. 2 times slower would be 0.5 over 1. Tomorrow I'll show you a nice demonstration of diffusion, a video of it. They do some cool, mixing of the gases. Despite the silly voices and stuff, you can go to this link and watch it now if you want. It's a YouTube video, or you can wait till tomorrow. I know you got a lot to do, so you'll probably wait for me tomorrow. Okay, so let's talk about deviation from ideal gas behavior. And so this whole slide, we've sort of been, assuming that gases will behave in a certain manner. That they will behave where if you increase the pressure, the volume goes down, increase the temperature, the pressure goes up. All of these laws, they follow the idea that gases will follow the KMT. Again, tiny particles. Now these particles in here, they have no volume of their own. They have no attractive forces. The problem is that when I do this PV equals nRT, I am neglecting those two factors. But in reality, they exist. And there's something called the Vander Waals equation. The same scientist who was interested in intermolecular forces, that's what this gas law extension really looks at. And we can see that this is PV equals nRT down here, but now with factors A and B. A standing for the strength of the forces of attraction between the particles, and B standing for the volume of the particles. You're not going to be required to do this equation to manipulate it, but you should know what A and B mean. You should know that there's some deviation. And so what we see is that, what happens when we start to mess with temperature and pressure on a gas? And what we see is the following. An ideal gas, no matter what the pressure is, and no matter what the temperature is, would behave the same. It would follow PV over RT. And it would give us 1 for 1 mole, because that's what this is equal to. But when we have gases that are not ideal, look at what happens. At a very high temperature, the gas deviates somewhat. And so we can see the best conditions are high temperature and low pressure. This is when you're most ideal. Look at what happens when we lower the temperature to 500 or to 200 and we increase the pressure. The gases skew from the ideal gas line here, and you end up with a huge deviation. And, eventually what happens is you're going to liquefy the gas. If you lower the temperature and you increase the pressure, you're going to liquefy the gas. And liquefying the gas happens because what ends up occurring is that the forces of attraction take over. Forces of attraction start to dominate. The gas forms a liquid, it condenses. If you were an ideal gas, guess what? That would never happen. You would never actually condense. So I always like to think of this like ideal vacation. My ideal vacation, it's hot out. I am just relaxing, it's the summertime, and I have no pressure. Nobody's telling me what to do. My ideal vacation is high temperature, low pressure. That's what I'm looking for. What you can see though is that when we deal with gases and we're at STP or close to it, 20 degrees Celsius, look at how ideal the gases behave. There's really very little deviation. The most ideal gas here is hydrogen and helium. Look at how close they are to the ideal volume. Heavier gases like carbon dioxide and chlorine, those deviate more. So another rule with this molar volume of gas at STP, gases tend to be most ideal when they're the lightest. Now, talking and going back to, something like diffusion and effusion, why do smaller gases move faster? Back in honors chemistry or Regents chemistry, you'll learn that, temperature equals average kinetic energy. But kinetic energy is 1/2 the mass times the velocity, the speed, squared. And I show that again down here. But these gases, they are at the same temperature. They have to have the same kinetic energy. So that means that this product, 1/2 mv squared, has to be constant for different gases. So something has to be different about them. If I take something like hydrogen, which is, 2 grams per mole, and I compare that to oxygen, 32 grams per mole, their masses are different. It means only one possibility exists, and that is that their speeds are different. And check it out, if we look at this graph here, we can see these different gases at the same temperature. This is showing you, I don't know what temperature they picked, but whatever temperature it is, these gases here, they have different speeds. So down here shows the speed, and over here shows the fraction. And you can see oxygen's moving much slower. Most of the particles right here of oxygen are moving much slower than hydrogen. It's moving much faster. Now, we used to do math with this root mean square velocity. They took it out of the AP. It's not in the IB. But just to show you what it's trying to say, it's saying that this root mean square velocity, the average velocity, is equal to the square root of 3RT. T is temperature in Kelvin. R is a different constant, it's not the one that we're used to, over the gram formula mass in kilograms per mole. I'll practice a problem with you in class just so you can see how the math works. But you'll see that these gas particles are moving very, very fast. You can see the numbers down here, and that's in meters per second. But they're moving at different speeds because they have different masses. Now, something that comes up that's really interesting that I just want to talk about is what happens if you have the same gas. So let's say that you have, gas X, and I draw a plot for it like this. And I do energy / speed, and over here I do fraction again. Fraction of particles. And let's say that this is at like 200 Kelvin. The IB and the AP expect you to know how to draw one of these when the temperature changes. How does the graph shift? So they expect you to know that. So let's say we increase the temperature. Well, what generally happens when we increase the temperature, if I change the color here, make it pink. So if we change the temperature and make it hotter, the curve will shift to the right and it will spread out. And so let's say this is at 500 Kelvin. So notice that it's spread out more and it's shifted overall to the right. The peak of it is here compared to here. But the overall spread of it is a lot more. And what if I slow down the temperature? Let's say I make it like, 50 Kelvin. So if I do 50 Kelvin, now the particles tend to loop together like this. And so this will be at 50 Kelvin. Now look, something important about drawing these is that there's always some molecules that are moving extremely fast. And there's always some that are moving very, very slow. You have to draw one of these kind of showing, all of the possibilities. Most of them are moving at a certain velocity or have a certain energy, but you have to include even ones that would be moving much faster. So this is a skill that you need to know. You need to know how to draw one of these graphs and show the difference between high temperature, low temperature. All right, so that's gases. I know I rushed here at the end. Tomorrow in class, we'll clean some of this up. I'll do some of the root mean square calculations with you. I will also go over how to do some more diffusion and effusion questions. And I will also talk to you more about vapor pressure, collecting gases over water, and partial pressure. We'll practice problems on all of this stuff. All right, and we'll watch that video. So thank you so much for watching. Remember, test is next week. Good luck.